see a lot of root 6s, which is good. Oh, I see a root 12. I see a 1.414. Okay. A root 6 and a root 6. All right. So a lot of interesting attempts.
I did my math wrong.
That's okay. That's all right. So did you also mean root 6?
Yeah.
Yeah.
Instead of 2 root 2 squared, I meant root 2 squared.
Yep. Yeah. That's fine. The only one I'm real curious, I'm going to show like the root 6 in a minute, but so you guys did the integral from 0 to 2 of the derivative to, because you're thinking then you'd have the antiderivative at 2 minus the antiderivative at 0. So you'd have this evaluated at 2 minus this evaluated at 0. Okay, what you're technically getting then is you're getting the y value at x equals 2 minus the y value at x equals 0. So, okay, all right, it's an approximation. I like it. Whoops. I'm frozen. I like it because it's kind of out of the box thinking, right? So whenever I've done this problem in the past, so we have y equals root x, and we're going from, so this is 2, right? So this would be root 2. So I've always just connected and drawn a triangle, right? And just found the length of the hypotenuse, so 2, root 2. So this length would be the square root of 2 squared plus root 2 squared, or root 6, right? Which is not a great approximation, but it's not bad, right? I kind of like the, what your approximation gave you was this length right here. It's all right. Something. So, anyway, okay. Today we are going to learn how to calculate arc length. Before we do that, though, we're going to talk for a minute. Yep. One example, and we might do all these on our calculator because we can. Okay, so section 8.1, arc length. Last section of the unit, right? Tomorrow's your big quiz. Test is when? Wednesday. All right. So we need to calculate a length of a curve, right? One way, when you are young, I don't know if you ever did this, is to trace the curve with yarn, right? And then you hold the yarn up to like a yardstick or whatever and see how long it is, right? Yeah, okay. So that's great. It's not, the most accurate method, and you can't really do it, when you're in a business unless trace with yarn. But anyway, yeah. So we need a method for calculating exact arc length, which we're going to learn today. So how do we derive the formula for arc length? This is one of those things that you don't have to actually write down if you don't want to. This is the where did this formula come from slide. All right? Okay. So when we need to calculate the formula for arc length, the first thing that we do is we just approximate the length of a part of the arc. So we just, pick a little spot. This length is delta x. This length is delta y. So our approximation would be the square root of delta x squared plus delta y squared, right? Okay. All right, so that would be the approximate length of a single arc, is the square root of delta x squared plus delta y squared. Change in x, change in y. All right, so you get the little hypotenuse of this triangle. Now, before we move on, we have to do a little algebra with this. So what we're going to do is factor out a delta x squared out of the root. Now, you're thinking it's not in both terms. No, it's not, but you can factor anything out, right? You just by dividing. So we factor a delta x squared out of this term, we get 1. Factor a delta x squared out of this term, you get delta y over delta y squared, delta x squared. And then when you pull it out of the root, it's the square root of delta x squared, which is just delta x. So we pull a delta x out of the root. Now, what do we want to do with it? Well, in order to make our approximation better, we need to make delta x really, really small, right? So, of course, we're going to take the limit as delta x approaches 0. When you take the limit as delta x approaches 0, delta x becomes dx. And when delta x approaches 0, that means delta y is also approaching 0, and delta y becomes dy. All right, so that gives us the length of a really, really teeny, teeny, tiny arc. Like so tiny it's a dot, right? So now we've got this dot, and what do we need to do? We need to add infinitely many of them. Well, what gives us an infinite sum? An integral, right? So now to get the whole thing, we take the sum of all of these, which gives us the formula for arc length. So arc length, which from most books, like our old book, our new book, everything, most things online call arc length S. I don't know why they call it S. S for, because it's a curve, like a snake. Okay. All right. Yeah, Mahika.
So the second number 1, it says we should factor out a delta x, but then in the formula we factor out. So why isn't it like?
So I pull the delta x out, right? So delta x is the square root of delta x squared, right? So what you're really doing is dividing each of these terms by delta x squared. Does that make sense? Okay. Because you're inside the root. All right. So formula for arc length, in all honesty, they're exactly the same. I tend to, in my head, memorize it as the square root of 1 plus f prime squared. So that's what my brain thinks. When it's arc length, it's the integral from a to b of the square root of 1 plus f prime squared. This formula is important. It's easy. It's easy to use. You'll find, like, we'll do some setups today, and you'll find that they're pretty straightforward. You'll use this again in BC when you have to find things like distance traveled in 2 dimensions, kind of a stuff, right? So you'll learn distance traveled is basically the same thing as the length of a curve, right? The length of the path that's traveled, you just call it a curve, and you find the length, right? So arc length is really it's very similarly related to distance. And so when you get into parametrically defined curves, you will use a formula very similar to this for your arc length. We also are using this exact same formula right now in Calc 3 to do what are called line integrals, which again, you're following some curve in space, and not just calculating the length of the curve, you're doing stuff with it, but one of the things you can do is you can find what's called a lateral surface area, where you take some random curve and then you hang a curtain down and you find the area of the curtain like hanging from the curve, right? So anyway, that uses arc length also. So a lot of different things use the arc length formula. Okay, so we're going to start by redoing the warm-up. Find the length of y equals root x from x equals 0 to x equals 2. Calculators are permitted. So when you set these up, so it's the square root of 1 plus something squared. What are your limits? 0 to 2. Okay, so our function is, this is the same as f of x. So y equals root x. So take a second and find y prime. which you can write as 1/2 root x. So 1/2 root x. And then go ahead and put this in your calculator. See what you get. Oh, really? Oh. Really? What'd you get? 2.562. How many of you have an 89? 1, 2, 2. Oh, no. Just one of you has an 89? Okay. So, just so you know, there's an arc length formula on the 89. So, okay, I got it. This morning. You know, under your math,
What is it? What is it?
So, yeah. All right. You still have to do the setup, and this is going to be the majority of the points, right? Guys, she only gets the 89 just helps her get this faster. It does, like she still has to write the setup. So.
Yeah, that's probably.
Yes, and the test too. All right. Okay, so this one, you could do this dx or dy. Makes no difference. So whether you want to do this dx, if you do it dx, you have to solve this for y in terms of x and use x values. If you do it dy, you'd solve for x in terms of y and do y values, right? But you can get the same answer either way, whatever floats your boat. So so if you guys want, like, if someone wants to be daring and try this dy, feel free. Just so you know, it says no calculators. Let's just ignore that. And what I want you to do is do setup and then find the answer. Rashmi, so let's check your setup. So if you do it dx, what are your limits? 1 to 4. Don't forget when you're typing in your calculator to put the root. Right? Don't forget the root. 1 plus. So for this upper arc, if I solve for y, I get x to the 3 halves. It's really plus or minus, but since we're only doing this positive part, you just need the positive. So so our y prime, I'm going to come down here. So y prime would be 3 halves x to the 1 half. So you'd have 3 halves root x quantity squared dx. Okay, so if you put that in your calculator, I got 7.6337. Something like that. Any questions on that? Did anyone do it dy? Yes, you did? Did you get the same answer?
Yeah.
Yay! So if you did it dy just for fun, you'd have, you'd use what limits? 1 to 8, square root. So we would solve it for x in terms of y to get x equals y to the 2/3. So x prime would be 2/3 y to the negative 1/3. And you end up with 1 plus 2/3 y to the negative 1/3 quantity squared dy, which still gives you 7.6337, right? Either way. Okay, let's do one more. And now we're going to skip this. Okay, so we're going to do a quick thoughtful Thursday, and then we have one more. All right. Okay. One last topic. This is the last topic of the unit. And just so you know, this is not on your test. It's in your homework. It's super easy. So all it is, it's talking about arc length as a function where if we have, if we're doing y equals root x, right? Instead of having the arc length go from like 0 to 2, we could write the arc length going from 0 to x of 1 plus f prime squared. But instead, remember that this and this cannot match. So if you're using an x up here, you have to use a t or something else in here, right? So anyway, so what does that mean? That means your input is now this upper limit. So this just gives you an arc limit from 0, an arc length from 0 to whatever your x value is. So if I want the arc length from 0 to 1, I put in a 1, right? If I want the arc length from 0 to 2, I put in a 2, right? And so forth. And it's just turning your arc length formula into an arc length function where you put in an x value and you get out an arc length. So on that function, where the function itself is kind of static and the input is how far you going on the function. So all that being said, so this is not, this is not an FTC part 1. Even though there's a variable in the limits, we're not doing a derivative, right? So this is just a regular old set it up and be happy. What? The rate of change of the arc length? That actually sounds a lot like curvature, like concavity, kind of almost. Anyway. Okay, so all you have, like your last task is to write an arc length function that would give you the length along this curve starting at this point to some value x. So see if you can write an arc length function for that curve. Oh yeah. I told my students in Georgia that I was moving to Minnesota, and I said something of some kind of a phrase like, all right, I have to go to the office, and they all went, go? You have to go to the office? They don't talk like that, but some people do. Like I have some relatives in Minnesota who do have like heavy Minnesotan accents, or not accidents, accents, but not many.
Did they say like oh-ish?
Oh-ish?
Oh-ish.
Oh-ish? No. No. If they say, oh my gosh, what does my mother-in-law say? I can't think of her expression. It's, I'm drawing a blank. But yeah. No, just like my students in Georgia, none of them had Southern accents. It's just that common. So, which I guess is kind of sad. We're like eliminating the accents in the country, I think, you know. Even where? There's quite a few. What's your upper limit? X. What?
2x.
All right. So 2x minus 1/8 times what is the derivative of ln x?
1 over x.
1 over x.
Don't you need to do?
Oh, it's not. Oh, thank you. Undo. Oh, I just got to erase it. Okay. T plus 1 over 8t squared. Oh.
Minus. Oh dear.
Okay, third time is charm squared dt. Okay. All right. So, that's it. The main thing that you need to walk away with today is being able to just set up and calculate an arc length for a function from some between two x values. Okay. All right.